Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, course outcome and Bloom's taxonomy related to this topic is course outcome number 4, and the course outcome is apply the knowledge of theories of failure, shear force, and bending moment relations for analyzing the flexural stress, shear stress distributions, and the failure of beam sections. The Bloom taxonomy level is apply level. So for circular section, there are two figures, figure A and figure B. Figure A represents the diameter of circular section. Circular is d diameter, and area of the section is pi d square by 4. But the radius of the circular section is r, and there is a EF here. It is EF is at a distance of y from the neutral axis, where O is the center and R is the radius, that is radius OE, and EF equal to 2 times EB. We know the shear stress distribution formula, that is tau equal to FA y bar by IB, where F is the shear force and A y bar is the moment of shaded area. The shaded area portion is EF portion. This is the shaded area portion about neutral axis, and I is the second moment of area of the circular section, whole circular section, and where B is the width of the beam at the level EF. Now we are going to calculate what is the shear stress distribution of this section, that is the circular section. We are considering the formula for shear stress is F A y bar by IB. I is the moment of inertia of the circular section, that is I equal to pi d power 4 by 64. Where B is the width of the beam. We are going to calculate A y bar. So that A y bar comes from, it is integral part of dA y dA. So what is the elemental area dA? After calculating dA, substituting here y dA and integrating, that integration gives the whole section. So dA equal to, for that how to calculate dA? The dA is elemental area. So this elemental area, now for that what we are going to do is that we are considering a strip of thickness dy, at a distance y from neutral axis. Let dA is the area of the strip. The area of the strip is dA. Then what is it? dA comes from B dy. We are considering the small tip, that is a rectangular strip, that is the B dy. B is the width, dy is the thickness. So width into thickness, that is the B dy. That B dy is nothing but what is the EF into dy. So what is that? EF equal to 2 times EB. Substitute in the place of EF 2 times EB, 2 times EB dy. dA equal to 2 times EB dy. What is that EB? EB comes from, this is the right angle triangle. This EB, OB is the y and UO is the R. The EB comes according to Pythagoras theorem, R square, that is hypotenuse square, equal to adjacent square plus opposite side square, square of the opposite. Now R square, that EB equal to R square minus Y square. EB equal to under square root of R square minus Y square times dy. Now moment of this area about neutral axis, that is dA into y, that is y dA. What is the dA here? 2 times under square root of R square minus Y square dy, and dA equal, that is dA equal to 2 times under square root of R square minus Y square dy is the term, and y dA. Now this term becomes 2y under square root of R square minus Y square dy. This is the moment of this area, that is dA about neutral axis. We want total area. For that what we will do? We will integrate that integral of YdA is nothing but AY bar. So we have to integrate from which portion to which portion. This is the total portion we want, that is Y2. That is Y2. What is the total distance? This is radius. This is the radius here. This is also radius. This is also radius. These are all radius. So from Y portion to Y2 dA, if you make it, then we'll get it the total moment of area about neutral axis. That is integral Y to R, capital R, 2y times and the square root of R square minus Y square dy. Now here integrating minus of minus plus. So minus of 2y times R square minus Y square dy. Now further simplification. Now minus 2y is the differential of R square minus Y square. Why it is R square minus Y square? This is minus 2y. Now hence the integration of the above equation, it becomes minus of R square minus Y square whole power 3 by 2 by 3 by 2. This is integral of x power n. That is x power n dx equal to what? X power n plus 1 by n plus 1. From that concept, we use it here. We use it from, like we solved. We resolved that is minus of R square minus Y square power 3 by 2 by 3 by 2. That is minus y to r. After substitution and simplification, y and r square, then final simplification comes ay bar equal to 2/3 of r square minus y square power 3 by 2. Substitute this ay value in the equation of, that is the shear stress equation, F A y bar by IB. This AY bar, in the place of A by R comes 2/3 of R square minus Y square power 3 by 2. After substitution and simplification, again, what is the width B equal to? Width B is nothing but EF. That EF equal 2 times EB. What is the 2 times EB? 2 times R square minus Y square. In the place of B, substitute. It is 2 times under square root of R square minus Y square. Now, here, this is the term 2/3 of R square minus Y square power 3 by 2 is the term. That is, what is the term is? That is AY bar. F AY bar by IB. That is IB B equal to 2 times under square root of R square minus Y square. And simplification, final equation comes 2 times square root of, that is F by EI, F by 2i, F by 2/3 will comes, then F by, after simplification, the equation comes as, this is the equation, tau equal to 2/3 of F. Just let me simplify it, then you'll understand better. That is tau equal to 2/3 F times R square minus Y square power 3 by 2 I times 2. Then 2 times R square minus Y square power 1 by 2. Now 2/3 2 by 3i into 2 into F, that is R square minus Y square 3 by 2 minus 1 by 2. Then it is 2 get cancelled, F by 2 times, yes, then it becomes F by 3i times 3 by 2 minus 3 by 2, that is 3 minus 1, 2 by 2, that is R square minus Y square. That is F by 3i, is the 3 value, not ei. There is no modulus of velocity. Now this is the formula, the tau equal to F by 3i R square minus Y square. This is the shear stress formula for circular section. This is F by 3i times R square minus Y square. Now this is the total formula for circular section, that is F by 3i times R square minus Y square. If you want shear stress, maximum and minimum. So if y equal to 0, then the shear stress becomes maximum. Substitute in this equation y equal to 0. Then we can observe the maximum shear stress. This maximum shear stress value comes F by 3I times R square. So this F by 3I times R square, it happens where y equal to 0 means that is neutral axis. At a neutral axis, the tau maximum, the tau becomes the tau maximum. Now one more thing, what is the shape of the curve distribution? This shear stress is dependent upon the value of the y square. If the y square value increases, the shear stress value decreases. If the y square value decreases, the shear stress value increases maximum. So if y equal to 0, that shear stress is the maximum shear stress. That's why here the maximum shear stress equal to F by 3I times R square. What is that I here? F by 3I times R square. Now that I equal to, again for circular section, I value becomes, that is F by 3I means pi d power 4 by 64. In the place of the d, substitute 2r. Then it becomes pi r power 4 by 4. Substitute back in the place of I in this equation. In the place of I, the value of I is pi r power 4 by 4. Then simplification, after doing simplification, it comes maximum shear stress equal to 4/3 of times F by pi r square. 4/3 times F by pi r square, F by pi r square. Now one more thing, this is the maximum shear stress. Where it will be minimum shear stress? The minimum shear stress happens at y equal to r, at the top edge. Suppose y equal to r, then the shear stress is 0. And the variation of the shear stress is parabolic shape. The shear stress varies parabolically across the section, circular section of the beam. Why here? The shear stress is proportional to y square of y. So it is a parabolic variation. That means non-linearity. It is not linear variation. That's why the figure B indicates at the extreme R, it is 0, tau equal to 0. At a neutral axis, the tau becomes maximum F by 3I times R square. This is the maximum. So the shape if you draw, that is the parabolic. That is the figure B. The figure B indicates the shear stress variation or variation of the shear stress across the circular section. Now, F by pi r square, what is the tau average shear stress? Now, average shear stress equal to shear force by average area. Shear force by area of circular section. The shear force is F by area of circular section, that is pi r square. This F by pi r square is nothing but average shear stress. Substitute in the place of tau maximum equation. The tau maximum shear stress equation is 4/3 times F by pi r square. This F by pi r square is average shear stress. Now tau maximum equal to 4/3 times average shear stress. That means maximum shear stress equal to 4/3 means 1.33 times average shear stress. So the maximum shear stress is how much percent is more than the average shear stress? That is 133.3% more than the average shear stress. So the question it will be asked in examinations that derive the shear stress equation, the maximum shear stress equal to 4/3 times 4/3 times average shear stress of a circular section. Now next, how to apply this formula in problem, how to use this formula in problems, how to apply this. Now the problem here it is that we have to find out average shear stress and maximum shear stress, and also the shear stress at a distance of 40 millimeters from neutral axis. It is at a distance. This 40 millimeters indicates why. If we know the average shear stress, the average shear stress equal to F by pi r square. The maximum shear stress equal to 4/3 times tau average. And we want at a distance of y. What is the distance of the y formula? The distance of the y, that is tau equal to F by 3i times. F by 3i times r square minus y square. These three formulae we have to use in order to find out the objectives which were given in this problem. So what is the problem? Let us read here. A circular beam of 100 millimeter diameter. A circular beam of 100 millimeter diameter is subjected to a shear force of 5 kilonewtons. Is subjected to a shear force of 5 kilonewtons. That is the value of the F, shear force. And the diameter D, that is the diameter. From that, R comes, R equal to D by 2, that is 100 by 2, that is 50 millimeters. So what to be calculated? The calculation is that first average shear stress, second maximum shear stress, and the third one is shear stress at a distance of 40 millimeters from neutral axis. This 40 millimeters from neutral axis, that is 40 millimeters is y. Now let me represent in graphically. This is the neutral axis. This is the neutral axis. Again, we want at a distance of what 100 millimeters. That is this is y is 40 millimeters. This y is 40 millimeters. And what is the radius here? The radius here it is 100 by 250 millimeters. So we know the direct formula. Otherwise, we can derive this from the what is the proof which derived the shear stress variation across the circular section. That is the variation of the shear stress across the circular section is F by 3i times r square minus y square, where r is 50 millimeters, y is 40 millimeters, F is 5 kilonewtons. One more parameter is required in order to achieve the distance. That is shear stress at a distance of 40 millimeters. That I, this I comes pi d power 4 by 64, where d is here 100 millimeters. After substituting, we'll get it the value of moment of inertia of a circular section, of the whole circular section. Now, what is the first objective? The first objective, yes, the data given. First, write down the data which was given. The data given here it is D, that is diameter of circular section is 100 millimeters. What about R, radius of the circular section, that is 100 by 2, that is 50 millimeters. F, shear force, the shear force is 5 kilonewtons. 5 kilonewtons is nothing but 5000 newtons. Now average shear stress equal to shear force by area of circular section. What is the shear force? 5000 newtons by what is the area of section, that is pi r square. What is the R value? 50 millimeters. Pi into 50 square. 5000 by then pi times 50 square, that is 0.6366 Newton per square millimeter. That is the first objective. What is the maximum shear stress? We know the relation between the maximum shear stress and average shear stress. That is tau maximum shear stress equal to 4/3 times tau average. We found that average shear stress after substitution of the average shear stress, that is 0.6366, 4/3 by 4 by 3, 0.6366, that is 0.8488 Newton per square millimeters. Average shear stress. What is the here? The shear stress at a distance of 40 millimeters from neutral axis. The distance at the shear stress at a distance of 40 millimeters from neutral axis. How to find out? You know the relation, that is F by 3i times r square minus y square. The r value is 50, y value is the 40. The shear stress value, that is the shear force, that is 5000 newtons times 3i pi d power 4, pi into 100 power 4 by 64. After simplifying, after substitution and simplifying, the observed a calculated value of the shear stress, that is 0.3055 Newton per square millimeter. Let us tau average shear stress equal to 0.6366 Newton per square millimeter. Tau maximum equal to the maximum shear stress, that is 0.8488 Newton per square millimeter. The variation of the shear stress at y distance at 40 millimeters, that is 0.3055 Newton per square millimeter. Now, based on these results, if we draw a curve, yes, it is not asked, but we can represent the completely the circular cross section, how it is varying. The maximum here it is variation. Here it is ends 0. The maximum shear stress takes place at the neutral axis. This is the neutral axis. Here it is. The maximum value is 0.8488 Newton per square millimeter. One thing is that the shear stress, wherever we consider within the radius, substitute if r equal to 30 millimeter, 30 square millimeter, the maximum radius is it should be within the range, and 10 millimeters, 20 millimeters, 30 millimeters, 40 millimeters. And if it is 50 millimeters at a distance of 50 millimeters, then it becomes shear stress becomes 0. This is the shear stress at a distance r, at shear stress equal to 0, where r equal to 50 millimeters. And here, when r equal to, what is the radius here, at the neutral axis, at y equal to 0, this is the position y equal to r, this is the position at y equal to 0. So the values, the shear stress variation varies. In this problem, the shear stress varies from 0 to TO2. Shear stress varies from 0 to the maximum value. What is the maximum value here? 0.8488 Newton per square millimeter. Is the meaning in this problem. Okay. Now, one more problem. Let us solve same model. Yes. A circular beam of having a diameter 105 millimeter diameter is subject to a shear force of 5 kilonewtons. Again, what to be calculated? Number one, objective one is average shear stress. Objective 2, maximum shear stress. Also sketch the variation of the shear stress along the depth of the beam. How the shear stress variation takes place along the depth of the beam. That means variation of shear stress is parabolic variation, parabolically varying curve. Parabolic curve takes place. So let us draw first how to start. Given data. What is the given data? The data was given. That's the first step. That is the diameter 105 millimeter. Radius equal to d by 2. That is 105 by 2. That is 52.5 millimeters. And shear force F equal to 5 kilonewtons. That is 1 kilonewton equal to 1000 newtons. So 5000 newtons. Next, objective 1. What is that objective 1? Here it is. Average shear stress. The average shear stress equal to shear force by area of the cross section. That is pi r square or pi d square by 4. What is the radius here? For shear force 5000 newtons divided by pi times r square. What is the r value? 52.5 whole square. This value gives the average shear stress. Then objective 2, the maximum shear stress. Maximum shear stress equal to 4/3 times average shear stress. 4 by 3 times, what is the average shear stress? That is 5000 divided by pi times 52.5 whole square. Now, after calculating these values, how to draw the sketch? Take a scale, that is the diameter, you have to draw with a radius of 52.5 millimeters. Draw a circle. This is neutral axis. The tau maximum comes, that value substitute, take a scale and draw a curve parabolically. Here where y equal to r, the tau equal to 0, shear stress equal to 0 at y equal to r. The shear stress is maximum at a neutral axis. Is the maximum stress value, substitute here. That is the tau maximum. Next, then again shear stress equal to 0 at y equal to r. We know the shear stress variation formula, that is F equal to tau equal to F by 3I times R square minus Y square. Here it is not asked where to find out what is the shear stress variation at particular distance. Only 3 objectives. First objective is average shear stress. Second objective is maximum shear stress. And third objective is that we have to sketch the variation of the shear stress across the circular cross section or depth of the beam. The depth of the beam, this is the depth, how it is varying. So parabolically variation is observed in the case of circular cross section, the shear stress variation. So the observed average shear stress, you can observe here it is. That is 0.577 Newton per square millimeter. And the maximum shear stress you can calculate as 0.769 Newton per square millimeter. The maximum value of the shear stress here 0.769, and the average value, it comes the average, but here the shear stress variation from top edge to bottom edge, that R for top and bottom, that is at y equal to r, the shear stress equal to 0 at y equal to r. So in this manner we can solve the problem of the shear stress variation across the circular cross section of the beam. Next, so we already solved this problem, this question, that in examination they'll ask that prove that the maximum shear stress in a circular cross section of the beam is, the maximum shear stress of a circular cross section of the beam is 4/3 times the average shear stress. So before we have calculated, the solution for this question is, this is the solution. We have to start drawing the shear stress distribution curve. That is the proof. Yes, from this begins. This is the solution for that question. Prove that the circular cross section, the maximum shear stress of a circular cross section is 4/3 times the average, 4/3 of the average shear stress. For that question, answer is, you have to start writing figure. You have to write and how the figure indicates, and EF and Y is the distance from neutral axis to the EF, and hatching area is, EF is the hatching area. What is the shear stress equation? The shear stress of any section, that is tau equal to FA Y bar by IB. Okay, from that we have to begin and step by step elemental area. First to find out AY bar. First to draw the diagram, find out elemental, that is moment of inertia, that is AY bar. That is AY bar, that is integral YdA. How to find out YdA? We know Y and dA is the elemental area. After that, if we integrate from Y to capital R, that is it is varying, then we will get it, that is AY bar. Substitute this AY bar in the shear stress variation of any section, that is F equal to, tau equal to FA Y bar by IB. In that AY bar component, you have to substitute of a circular section. And also one more is there, I, what is the moment of inertia of the whole section of the circular section, that is pi d power 4 by 64. After substituting all these things, then we can get it how the shear stress, the variation, that is tau maximum equal to 4/3 times tau average shear stress. Okay, so we have to solve in this manner, and we are going to solve few more problems based on for this model. If the given data is, first determine average shear stress and average shear stress and maximum shear stress of a circular section beam for the following data. Diameter of a section of a beam is 120 millimeter. Shear force is acting on the beam is 10 kilonewtons. Also draw the sketch of the variation of shear stress. So this is the problem. Then how to solve? Let us begin. For the given data here, diameter of a beam. The diameter of the beam is 120 millimeters. What is the radius of the beam? That is d by 2. That is 120 by 2. 60 millimeters. So if you want to represent graphically to understand, this is neutral axis, we already solved the problems. The tau derivation, we understood that maximum shear stress can be observed where the neutral axis is the tau maximum. Here it is tau 0. The variation of the shear stress across the section of the beam is parabolically varying shear stress. Now, what is the first objective? The first objective mentioned average shear stress is the first objective, and the second objective is the maximum shear stress. If we know the value of average shear stress, the maximum shear stress can be calculated by substituting in the relation of maximum shear stress and average shear stress relation. First to begin that average shear stress that equal to F by pi times R square. That is F was also given the shear force, that is 10 kilonewtons, that is 10,000 newtons. So 10,000 by pi times R square. What is the R is here? 60 into 60. Now 100 by 6 pi is the value of average shear stress. And maximum shear stress, the maximum shear stress equal to, what is the maximum shear stress? 4/3 times average shear stress, that is 4 by 3 times 100 by 6 pi. If you simplify it further, 4 here, it is 2 2's 3 times, then it is 200 by 6 pi, that is Newton per square millimeter. Okay, so that means here the value of average shear stress value 4/3 times here, 6 into 6, 36 pi, 100 by 36 pi, and here it is 36, then you have to change calculation, then it becomes 18 times. Okay, here 4 we can make it 9 times, that is 4 get, that is 27, 100 by 27 pi Newton per square millimeter. This is 100 by 36 pi, it is 100 by 27 pi square millimeter by Newton per square millimeter. So the average shear stress and the maximum shear stress, here it is varying parabolically, and the variation of the sketch, this is the sketch we have drawn here, the variation of the shear stress across the section of the beam. Okay, so let me conclude in this session. In this lecture we have studied the variation of shear stress across the circular section of the beam, and we have derived the shear stress equation for circular section of the beam, that is shear stress equal to F by 3I times R square minus Y square, and also found the relation between the maximum shear stress and average shear stress. The maximum shear stress equal to 4/3 times average shear stress, and applied those derived formulae and in the problems, and calculated the average shear stress, maximum shear stress, and the variation of the shear stress. These are the references were followed in this lecture, the textbooks and reference books and web references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.